Now we look at how we use the polar form of a complex number to find its power or roots. Okay, so let's first look at the problem of finding the power. And we have the general guideline. So if z is equal to r cosine theta plus I sine theta, then z to the power n is simply r to the nth and cosine n theta and plus I sine n theta. So now remember, we have how we found the radius or the modulus of the complex number. So we first start from 1 minus root 3i. And we find the radius again, the modulus is square root 1 squared plus root 3, negative root 3 squared, but that's the same thing. And then we have root 4, and that's 2. That's the same thing. But this time, we need to be careful because cosine, if we pull out 2, we see that tangent theta over here is going to be negative root 3. But cosine theta, we know, contributes to the real part is positive, and sine theta is negative. So we must have theta over here equal to negative pi over 3. Alright, so what it means is now we have 1 minus root 3i in the form of the polar form. That's a 2 we have, and cosine negative pi over 3 and plus sine negative pi over 3. I'll put I over here. So that's its equivalent form. So now what we have 1 minus root 3i to the 5th is going to be 2 to the 5th and cosine negative 5 pi over 3 and plus I sine negative 5 pi over 3. But of course, we noticed that negative 5 pi over 3 is not inside the principal value domain. So we look at an equivalent value because both cosine and sine functions are of period 2 pi, and negative 6 pi over 3 is exactly 2 pi. So what we have over here is the following. We just add 2 pi to it, and then this is going to be 2 to the 5th and cosine 3 pi over 3 and plus I sine pi over 3. So we actually get a very nice number, and that's going to be 2 to the 5th, and we have 1/2 and plus root 3 over 2i. So we have 2 to the 4th and 1 plus root 3i. So what it means is that 1 minus root 3i to the 5th, we don't have to multiply them out using the distributive law, but using this polar form, we can conclude that this is simply equal to 2 to the 4th and 1 plus root 3i. Alright, now let's look at the second problem, finding all the roots of a complex number, solving equations of this type. We can consider this also as an application of the polar form of the complex number. So again, we start from 1 minus root 3i, rewrite this one into the polar form. That was, we already did this one, so we can just copy it down from over here. So it's 2 cosine, and we had negative pi over 3 and plus I sine negative pi over 3. So that's the starting point. And then what do we have? We remember that we always have 4 roots if we are trying to find the 4th root of this number. So we need to expand this polar form a little bit more. This is going to be the same thing as cosine negative pi over 3 plus 2k pi. We know cosine is the periodic function of 2 pi. So if we add a 2k pi to this, it will not change its value. And sine also negative pi over 3 plus 2k pi. And that's how we find all the roots. And then z is going to be equal to, we have the formula, so it's going to be 2 to the power 1/4. Okay, and then we have cosine. This is the modulus part, and then the cosine part we divide by 4. So that's going to be negative pi over 3 divided by 4 is pi over 12. And this part, 2k pi over 4. Let's just keep it this way, and we can simplify a little later. And this is I, and sine again, negative pi over 3 divided by 4 is negative pi over 12, and plus 2k pi over 12. Or if we simplify a little bit, and that's going to be 2 to the power 1/4, and we have cosine negative pi over 12 plus k pi over 2 and plus I sine negative pi over 2 and plus k pi over 12. And k is equal to 0, 1, and 2, and 3. We have exactly 4 roots. Let's go a little bit further to see what kind of complex numbers we have over here. First of all these complex numbers, 4 roots, they all have the same modulus. That's 2 to the power 1/4. But the arguments are different. Let's look at all these 4 different arguments. So we have 4 roots. z1 is equal to 2 to the 1/4, and cosine, when k is equal to 0, is negative pi over 12, and plus I sine negative pi over 12. That's when k is equal to 0. And that's okay because negative pi over 12, this argument is the principal value. Let's look at z2. It has the same modulus, 2 to the power 1/4, and we have cosine. Now negative pi over 12 plus pi over 2, that will give us 5 pi over 12. 5 pi over 12. And then plus I sine 5 pi over 12. So that's the second one. And we can find the third one, and z3, and that's when you add pi over there, and then we have 2 to the 1/4. It's still the same modulus, and then we have cosine negative pi over 12 plus pi. That would give us 11 pi over 12, and then plus I, and sine 11 pi over 12. And notice that this value is still within negative pi and the pi, so this is fine. This is the principal value. So look at z4. z4 is going to be 2 to the power 1/4 and cosine. Now we have when k is equal to 3, so we have 3 pi over 2 minus pi over 12. So we have cosine 17, because yeah, that's right, 17 pi over 12 and plus I sine 17 pi over 12. But we notice now this value over here is greater than pi, so it's no longer in the principal values range. So how to find the principal value of this z4. We just simplify this a little bit. It's 2 to the 1/4. Remember, cosine and sine, their periodic function is 2 pi. So we actually subtract 2 pi from this one. That's going to give us cosine negative 7 pi over 12. Now it's within the principal value range. And I sine negative 7 pi over 12. We have these 4 roots. And if we want to graph them, and that's what we have. We have over here, start with the first root, negative pi over 12. Okay, and then this one over here, and we have actually perpendicular over here. This one over here, we will have this is angle over here, and this angle over here is 5 pi over 12. And then if we go to the other side, and this is going to be 11 pi over 12. That's the angle. And then we have another one over here. And then we look at this angle over here. That's the principal value of the angle. It's negative 7 pi over 12. So we have 4 roots of this complex number 1 minus root 3i.